Thank you very much for inviting me to this workshop. This really has been a wonderful workshop so far. And thanks for that kind introduction. So good afternoon, everyone. Today I'm going to talk about training end-to-end policies for autonomous driving. I'm going to shed some light on what I think is the defining challenge of this field. And it is, how do we evaluate end-to-end policies, not just in autonomous driving, but across embodied AI. The path forward in scaling up evaluation, which I believe is really through world models. So this is a typical street in London, right? The ego car is trying to drive up the street. There's a white truck that pulls out. There's a pedestrian who walked by. The blue car had its blinkers on. Fairly chaotic environment, but something which is not entirely unexpected in an urban setting. If you were to travel to almost any city in the world, this is the environment that a car faces, and this is the environment that you need to learn to navigate. What's particularly interesting about this problem is that every time you get an observation, you've never seen that observation before, and you'll probably never see that observation in the future. This is because the weather is unique, the location is unique, the actors are unique, the behaviors are unique. And so when you have this kind of very, very complex real-world environment, how can you create a policy that can take an acceptable action that can get you from point A to point B? I strongly believe that the way to create systems that are effective, that are robust, and that are generalizable is through creating streamlined architectures. And maybe I might make a stronger statement in saying that I believe that the only way to do this, to create generalized architectures, is to have them streamlined and simple. We've, of course, it's 2025, almost 2026. We've had several years of this working in NLP. We've seen success stories in vision. Multimodal AI is working much better with streamlined architectures. Yesterday, Andrea was talking about how the most simple transform architecture can now power something as powerful as VGGT. And I think this is also true in embodied AI. So at Wayve, we have a single neural network that can take in sensor inputs and can produce a motion plan. At Wayve, all our self-driving cars, many of you have probably taken a test drive at some point in a Wayve car. We only use RGB cameras. So we have 5 cameras, one that looks forward, 2 to the sides, and then 2 that kind of look at the back. And these 5 cameras really power all of our self-driving stack. Of course, streamlined architectures are not confined to using RGB cameras, and one can use other sensors as well. As we start having higher levels of autonomy with our self-driving cars, it is sometimes necessary to have redundant sensors. And so we've also started experimenting with adding radar and LiDAR and other sorts of sensor stacks in addition to RGB cameras. But once this neural network gives you a motion plan, there's a very, very simple verifier that makes sure that the motion plan is executable on the hardware that it is currently supporting. And then that's it, and that's how the car drives itself. It's always a good idea, of course, to have secondary systems, which are also end-to-end trained neural networks, in case one neural network does not react as quickly as you need to. You have this sort of safety subsystem. You can think of it like another teacher network with a handbrake at its disposal. If a child suddenly walks onto the in front of the car, the safety subsystem can activate the brakes. And so these end-to-end systems are trained with a lot of data that we get from our fleets and that we can get from our partners across the world. And they offer many advantages. First of all, they are not modular in nature by definition. And so you don't have to worry about training a large sequence of perception systems. And when you have modular architectures, you have to take care of many, many different neural networks that you compose into a self-driving system. And these can be expensive to build, expensive to scale, and they can be quite brittle. But I think the issue really comes in when you start, as human beings, thinking about architecting your systems as if you were going to, or based on how you guess humans drive. And so modular systems tend to have a lot of hand design rules, hand design interfaces, and they tend to be very brittle and clunky. The other things that a lot of modular systems require are combination of HT maps for cities, as well as high-end sensors like LiDAR that can allow you to localize yourself within these maps. What we do is we take RGB sensors and provide an action output, and it's completely independent of our knowledge of where we are in the scene. And so at the heart of the neural network is really powered by a foundation model, as now we've seen in many, many disciplines in AI. And so this foundation model is a model that is capable of doing things beyond just driving, right? And so this foundation model can take many different kinds of inputs, not just in terms of sensors, but in terms of modalities. So the foundation model that we built in Wayve can take in, obviously, RGB inputs. It supports different sensors like radar and LiDAR. It also supports other sort of visual intermediate modalities, like it can support taking segmentation maps. It supports language, and also outputs many of these different modalities. Not all of them are useful for driving. Some of them are useful for creating simulators. Some of them are useful for visualization. Some of them are useful for debugging. And the other thing that I want to point out about the foundation model that we build is we don't just use self-driving data that we collect from our fleets. We're also able to use what we call driving adjacent data. So data that is similar to driving that can teach you good representations that are useful for driving. And so you might have data collected by cameras of people walking on sidewalks. You might have cameras moving around in indoor factories and so on. And we find that all of this data does help create a better, robust representation. But then this foundation model is then post-trained for different tasks. And so when the car has to drive on the road, we take the foundation model, distill it down to the right size, and then post-train this on the task of driving. And this post-training can be quite light because most of the heavy lifting is done by the foundation model. But then once it is post-trained on a particular GPU in a car, any car that supports that GPU has essentially the same set of parameters. And so the model that we have is built for any car, anywhere in the world, with no HT maps, of course. And one can sort of have different requirements for the capabilities of these models. In self-driving, there are many different levels of self-driving. Level 2 is when you have a human being with their hands close to the wheel. Level 3 is when you have a human being in the driver's seat, but they're distracted, and so they could be on their cell phone, and you need to alert them when they need to take over. And level 4 is when there's no driver there. And so each of these have very different levels in terms of validation, but you can think of it as it's still a single set of neural network parameters for each of these different levels. So Wayve started in London. Technically it started in Cambridge, but it's been in London for many, many years now. And so all of our initial data, our initial testing has happened in the UK. And we found that the single neural network drives very well in the UK. But because it's a single network that is completely agnostic to where it is in the world, we were able to take this network a couple of years ago and drive the same network in the US. And so the US obviously is, in the US, people drive on the other side of the road, but there are certain rules and regulations that are still followed. You have to maintain the same sorts of distances, don't run over people, don't bang into people, don't hit the sidewalk, etc. And so remarkably, we found that zero-shot performance of a UK-trained model with no US data was actually pretty good, and it was a safe driver. But then the thing that actually gives you hope that this can actually generalize to the rest of the world is that with just 100 hours of data, you get roughly 5x improvement in performance. And when I mean 5x improvement in performance, what I mean is the number of times that a human driver has to intervene reduces by a factor of 5. 100 hours is nothing. You can have one car drive around for less than a week and you have 100 hours. So this is extremely trivial in terms of data collection. And then you go to 500 hours and then you start seeing 1 to 2 orders of magnitude improvement in success. And this has a network effect, right? So the US was the second country that we took our single neural network and put it on the road. And then the third country was Germany. And then if you look at zero-shot performance in the US versus add in the US data and look at zero-shot performance in Germany, unsurprisingly, as vision people, as ML people, we expect there to be a network effect, and it was very pleasing that we did in fact see this. And so zero-shot in Germany starts getting much better. And the hope that we have is that as we start getting even very, very, very little data across more than 100 countries, this will be a model that is capable of driving anywhere on any embodiment any time of the day. And so in 2025, we've had an ambitious goal of taking this car and testing this in 500 different cities in the world. I would say we're about a few hundred cities in already. We have, last I checked, we were more than 200, and maybe now we're already about 300 cities in the world. As I said, this is a single neural network. 1/3 of the cities are in our training data. And so, we have taken the car at some point in the cities. There's a tail distribution, of course. Some of those cities have maybe just a few hours of data. Another third of the cities are data that are not collected from Wayve, but are collected from several partnerships that we have with other companies. And so this is not truly zero shot, but it is still data that doesn't conform to the kinds of sensors that we use, the kinds of cameras that we use. And the remaining third are completely zero shot. So earlier this year at CVPR, we had the car in Nashville, and we have never been to Nashville before. And so we did take a few people out for a demo drive, and that was truly zero-shot performance. And so here's a sort of a quick video of the car driving through many, many different parts of the world. Some of these drives are what I like to say boring, and a boring self-driving car is a very good self-driving car where you don't have to worry about it. And there are some intersections that are particularly tricky to navigate. So this is a bit of a crazy intersection. I've never actually been here, but it's a nested roundabout. Not sure why people have designed this way, but it's there's a big roundabout in the center, and there are these little nested roundabouts. And I think the nested roundabouts are clockwise, but the regular roundabout is anti-clockwise. And so this is our sort of out of distribution test case where the car drives really well. And since we're here in France and having a really good time, feels mandatory to also show you that we're able to perform well in roundabouts in France. So I found this video of the car driving on the road quite interesting because there are no lane markings here, at least none that I can see. And there's cars going in front of you with, sometimes an indicator, sometimes not. But we find that the network that we have trained drives well. The other thing that we found is that it's very safe, but it's not slow. People find that when they sit in the car, they feel like it's driving at the speed that a good human driver would drive. And so we're certainly not at the threshold towards the extreme where, yes, we have no accidents, but we never get you from point A to point B. Okay, so that's how we build our our self-driving neural network. It's a single neural network. The beauty of having this end-to-end system is, in a sense, it sort of democratizes the creation of these models within the company. It's a nice streamlined architecture, and we have tens and tens of people working at Wayve who are able to change the data recipe, who are able to change, add in some auxiliary losses, change the kinds of layers that are added in the transformer, and perform experiments on a fairly regular basis. And so I would say in any given week, there's at least 4 or 5 new variants of the model that are created within Wayve. And this is a really good thing, and this has led to, in part, the fast progress that we've seen year on year, multiple orders of magnitude reduction in the number of times people have to touch the wheel. But the flip side is that it has made evaluation a bit of a nightmare. And that's because every time you create a model, you want to take it on the road. And now the models that we have, the best models that we have, are at the point where if you make any meaningful improvement, we need to drive several tens of thousands of kilometers before we can get any statistical significance in our measurements. And this is just not scalable. This is extremely, extremely difficult to pay for and to validate. If you take a step back and, so these are the kinds of scenarios that you want to test your car on. These are out of distribution. But you only encounter these so rarely. Yeah, go-karts on the road, sheep crossing the road. Yeah, you encounter them so rarely that evaluation and validation is a big concern at Wayve. So if you take a step back, there's a few interesting challenges when you think about evaluating these models. First of all, every time you have a model, and like I said, we have multiple models every week, you want to test them all over the globe, right? So we have offices now in many different countries, and we have partnerships with many car manufacturers out there. But it's just very expensive. We have interns on my team who will produce a new model. It takes a lot of money to test these models. The other thing is that because we are, the big claim that Wayve has is that a single neural network that can drive any car. Obviously, we have to test this model on many, many different cars. And new cars with cameras are being fitted. Every quarter I hear of, okay, there's this new model and we've put cameras on it. And so now we can't afford to test the network again on all of these embodiments. Robustness testing is a big thing. Sometimes the car will successfully navigate something extremely tricky. And we want to know, as scientists, we want to know, was this by accident or was this actually a good model that's able to navigate this, when the sun is glaring at the cameras. And so you want to be able to tweak small things in the scene. Then there's, of course, safety critical testing. So for example, these are what are called, sort of what if scenarios. And so you say, well, what if, the car started drifting towards the lane and you felt, at this point it's going to start hitting the oncoming traffic. Is your network able to self-correct, or would it actually have gone and hit this traffic? This is almost impossible to test in the real world, especially as your model gets good. Then there's, of course, out of distribution testing, this family of sheep crossing the road. And finally, there's targeted testing. So there are certain scenarios that you encounter as a human driver that are very frustrating. For example, there's a bus waiting to pick up people. It's been 2 minutes. People are getting on slowly. At this point, you really want to veer on the side and see if you want to overtake something. So how do you create scenarios like this without having to do this by hiring actors and hiring double-decker buses in front of you? And so I think the only way to solve this problem is through simulation. And people have been working on this for many, many years. In my previous role at AI2, I worked on procedural simulators. And procedural simulators, of course, give you an incredible amount of power, an incredible amount of controllability. But there's a huge sim-to-real gap when it comes to procedural simulators. And to do this for self-driving, we have to go beyond procedural simulators. And so I think the way to do this is through neural simulation, which is essentially to build world models. And so Wayve has been building what they call a Gaia series of models for the last few years. And each 6 months, we've been improving this series. And now what you see here are videos. All of them are synthetic. They're very natural looking, very realistic. And these models are now used to test driving models. So in a sense, you're taking a neural network, which is a driving model, and you are testing it inside another neural network, which is called a world model. Right? Of course, what you're seeing here is just one camera. In order to effectively test your system, you need to be able to simulate the entire environment. And so here I'm showing you 5 different cameras, because many of our cars have 5 cameras. But of course, we're now able to also simulate, for example, radar, because radar is a redundant system that we need to also attach to our cars for certain scenarios. And so you have a front forward, front left, front right, and the back cameras. The world model is obviously trained with a lot of data. It's a large model, but it is completely, in a sense, it is data-driven. There's very, very few heuristics in order to train this model. It would be quite sad if we believed in end-to-end learning for driving models, but modular systems for our world models. As I said, simulates the full environment. Agents are reactive. And each year, we are trying to make these world models more controllable. So, I mean, my vision for world models is that they should provide you with every controllable aspect that a procedural simulator gives you. You should be able to get a person walking in a particular way, turn around, go back to the curb. You want to be able to control every actor as you might as you're evaluating your. This is gone. Okay, we're back. Yeah. But of course, you want to do this in a way by which you can do this efficiently. As we know, video generation systems are very slow and very expensive to run. And so how do you create world models that are efficient to run? So we use a diffusion system. And diffusion system, of course, as many of you already know, needs to run in a compressed latent space. And so we have different kinds of tokenizers. Here is an illustration of one of the tokenizers that we have at Wayve. And so this is a video tokenizer that takes in a sequence of frames, compresses it into a latent space that makes the modeling problem a lot more tractable. And then you have a decoder that can take the latents and give you back frames. And so now these latents at training time are sort of, they're trained end-to-end in an encoded decoder architecture, but then the decoder is also used when your world model produces latents, and then you have to bring back latents into pixel space for the purpose of video generation. And so the goal of this tokenizer is to really get you high degree of compression. And so we have a high degree of both spatial and temporal compression. But importantly, it's also important for these latents to be semantically meaningful and be consistent, not just across a single video, but across every video in our data set. And so you want all of these representations to be as simple to model with your world model. And there's a finding that is now fairly well known in the field, which is that as you increase the complexity of your latent space, your compression factor goes up. And so you start patting yourself on the back saying that, oh man, now I can just train a 1 billion world model, it works. But as your latent space gets more complex, it gets harder to model. And so sometimes more compressed latent spaces require more parameters in your world model. And so a lot of our research goes into how do you create a latent space that can be highly compressible, but still quite easy to model from a world model perspective. At training time, you take a series of frames and then you compress them down to latents and then you decode them. But at inference time, we do this through a rolling window, which of course helps us with a lot more temporal consistency across the scene. And so here you can see that you can, as an illustration, you can take 3 latents, start decoding frames, and then with a sliding window, only decode a small set of subsequent frames so that there's some information passed on through time. And as you can see, the auto-encoded frames that come out from encoding and decoding latents, they resemble our input frames with an extremely high degree. We're able to reconstruct not just static objects, but dynamic objects really well. And then if you look at the first 3 principal components of some sort of a representation of your latents, then you can see that not just across frames, but also across videos, you see similar colors indicating sort of similar parts of the latent space to encode vehicles, to encode the road, encode the sky, etc. And of course, once you create this latent space, you can then use a diffusion model, which is a model that is trained to denoise noisy latents. And so you can provide noisy latents, and at each time step, you can denoise these latents given certain conditionings. And so as input, we provide a history of frames, and at output, the goal is to produce the next set of frames. But then the conditionings are of a various sort. And so we use an ST transformer, which means that you can have spatial attention, then you can have temporal attention, then you can have cross attention to your different conditionings. And so we're able to condition on various amounts of metadata that our videos come with. So you can condition, for example, on country, you can condition on weather, you can condition on time of day, you can condition on actors that are in the scenes, you can of course condition on the state of the ego vehicle, what speed and what curvature it is traveling, etc. And so based on these conditionings, you can now roll out different futures, and of course you can sample different futures based on different random seeds, and then you can have another model that can filter out to keep out bad quality examples and give you good quality examples. There are different kinds of training tasks that we use to train our diffusion models. This is an illustration of 3 of them. You can, of course, train diffusion models from scratch. You can train them from context. You can also train them on specialized tasks like in painting, which means that you have a video that you've collected from your car, and now you want to simulate what happens if I had 3 more pedestrians who were trying to cross the street from the side. What would this video look like? What we found is that to get the most generalizable world models, it's sometimes useful to train on multiple tasks, so to have pre-training strategies with multiple losses. But in practice, we find that we can create far more efficient world models, which are obviously important because we're running these at very high scales. To create much more efficient models, picking the right task is of prime importance. Hallucinating a completely new world is a much more complex problem than rolling out an existing world. And so the task that seems to work best and most efficiently is always the one from context. And this is, as we increase the amount of data in our fleet, we have been to most places in the world already, so we have some context that we can begin with. And then rolling out this context gets far more efficient. As with any other foundation model or large world model, training data is paramount. And so we've spent a lot of time in the last year to think about what kind of training data one can use to build this world model very effectively. And so now we have training data that spans multiple countries across 3 continents. We have North America, we have Europe, and we have Asia. We have diverse embodiments, diverse environments, and our emphasis is really on how do you sample this data in order to create effective pre-training checkpoints. And so we found that we need to sample on a variety of criteria, not just on the speed and curvature, but also on different elements that are present in the scene. And for this purpose, sometimes we use different perception systems, like object detectors and VLMs, in order to understand what's happening in the scene, such that we might be able to sample interesting things that you can put into these world models. And so when you do this and when you train this at reasonable scales, you really can start simulating videos and driving scenarios from across the world. So in this video, each row is a particular scenario. Each column is a different camera, and you can see that we can start simulating videos from across the world at daytime and at nighttime. If you notice here, a lot of the videos that are here are videos on highways, and highways typically tend to be much easier to simulate. There's, of course, the camera is in motion, and there are some vehicles that are moving across you, but the overall scene complexity is, I would say, for 2025 world modeling, the overall scene complexity is, I would say, medium hard, right? But the most interesting points where we want to test our systems are in more complex scenes. So here's a scene in an urban environment. You can see a bicyclist is crossing the road. There are people walking on the sidewalk with an umbrella. I don't know if you noticed, but there's some sort of a subway going on top. There are signs here. There are road signs on the side. And these are the sorts of features that start becoming more and more complex for us to model. And so here is a world model, a previous version of our world model, and you'll see that it struggles at many of these different things. So, the bicycles look weird. The train has disappeared. I mean, the people you feel like the people are just zombies that are floating in space and so on. But then we keep making improvements to our models. And so here's a sort of a sneak peek to our one of the latest checkpoints that we've got. And so you can start seeing that things are a lot more realistic. High frequency components such as wheels moving on the road, people walking on the streets, are far more realistic. And this really plays a very important role in reducing the sim to real gap, because after all, a driving model is the consumer of this data. And the things that, what I could say in terms of like making improvements to world models is, you really have to think about the tokenizer first. As I said, simply having an extremely compressed space doesn't mean that the world model can solve these problems with a limited set of parameters. And so we've spent a lot of time rethinking how we build tokenizers. Data, of course, is key, and so we've rethought how do we sample data so that we can expose these kinds of scenarios to a world model, and then, of course, scale does help with most things. Another very interesting thing that that people who build world models tend to think about quite a lot is how do you get this thing called world on rails capability. So when you train world models, you generally train them on driving data that you have in your fleet. And so the Wayve fleet is full of driving data that is obtained from human beings who are extremely good drivers, right? They are people who Wayve has hired, who know not to break rules, not to get into accidents. And so we've built up, thousands and thousands and thousands of hours. And so we use this to train our driving models, and we also use this data to train our world models. And one interesting thing you see is that if you're sort of simulating the world in this world model, and you suddenly give it an action that goes towards the opposite end of the road, the world model will simulate the cars who are about to crash into you. The cars slow down and let you make that left turn. And so it's very, very difficult to get these world models to drive badly because they've never seen bad behavior. Whereas what you want to do when you evaluate driving systems is place your car in unsafe scenarios. So in a sense that you want to do everything that's against the intuitions of the world model. So this is what we call world on rails capability, which is that you take a video that you have from the real world, and you're able to simulate a scenario where you take an action that is not present in the real world, but everyone else, in the sense, goes on rails, which means that they take the same actions that they did in the original video. And this really allows you to test, as you start drifting towards a lane, are you able to come back, right? So here's a bit of an extreme example that we created recently that's quite indicative. So here the sun is, at this particularly poor part of the horizon when it comes to driving. There's glare on the driver's face, and of course there's glare on the cameras. And so as there's glare, looking at the lane markings becomes harder and harder. And so these are the kinds of scenarios where the driving model can tend to start drifting. And when you're going on the highway at high speeds, a small amount of drift can put you in a very dangerous situation. And so now what you really want to do is you want to actually put this car in unsafe scenarios going towards the sides of the road, but you don't want other cars to move away from you. You want other cars to go exactly where they were going. And so now we've been able to post-train our world models to have world on rails. So what you see here is the ego car, and we're just going in a little bit of a sine wave just as a demonstration. The ego car is now moving, but the other cars are exactly where they were in the original videos. And this is actually a very, very interesting and cool capability that is going to really power a lot of evaluation and validation scenarios in the company. Yes, you will still see lots of visual artifacts. This is still a research project that is still in motion, but you can see that there are the beginnings of world on rails capability. That's quite exciting. Of course, that was about controlling the ego agent and keeping everything else constant. You also want to do the exact opposite, where you want to keep the ego actions constant, and you want to introduce other actors who might lead you to unsafe scenarios. And so we have the ability to have 3D boxes drawn on the video, and then the world model is able to create actors at the locations of those 3D boxes. I think this is just the beginning. I think drawing 3D boxes on videos is interesting, but it is actually very difficult to use. And so the way I see this is we should be able to do this through a combination of language, through a combination of boxes, through a combination of just drawing a trajectory on the screen. Think of it like anything that you can do in Photoshop, you really should be able to do with a world model. And then, so when I listed out the 6 challenges, this was one of the challenges that we've been facing in the company is we've collected all this data, we've trained these driving networks. Some of this data is used in validation, but I've collected this data with an old version of my car, and now I have a new version of the car with sensors placed in slightly different locations. How can I now get data for this? And so this is what we use the world model to do as well. And so because the world model is essentially something that can render pixels on the natural image plane, you can give it conditionings based on another video, give it the same sort of action conditionings that the ego vehicle takes, set some constraints based on transferring pixels from one set of cameras to the other set of cameras, we know exactly where the cameras are on the embodiment, you can start taking a video and simulating it as if it were captured through a different set of cameras. So here it's placed on a car where there's a little gray bar that occludes part of the scene. And so now you can have a source camera rig and you can transfer this video to this target camera rig. And we're starting to use these capabilities in not just evaluating different models, but also taking models for which, cars for which we have almost zero training data, getting a little bit of training data through camera rig transfer, and then post-training these models. Another capability that we've been able to develop is a capability to be able to condition these models on embeddings. And so now you can take a video and you can generate an embedding through some, let's say, a dyno feature or a clip feature or some feature that can take embeddings of different frames. And now you can condition a world model to input an embedding and generate another scenario that is very, very, very similar to that scenario. But then because your noise, your sampled noise is now different, the video that you generate has a sort of different appearance, but everything else is in the same position. Another way to do this is to do think of it like style transfer. So you can take an RGB camera feed that you have from the real world, and you can create a depth video through some monodepth model, and now you can train a model that can take depth and produce RGB, but now respecting all of the conditions that you have. And all of these things we do by simply post-training a world model. So we don't have another model that is depth to RGB or RGB to depth. We can take a world model that understands the natural image manifold, and you can post-train it. Sometimes you can post-train models that have only seen RGB and introduce depth in 4 nodes for 1 day, and these capabilities can be very, very, very easily obtained. And so here, for example, you can see that the video is really, really identical, except either you've changed day to night, you've changed the location of the sun, you've changed the appearance of the vehicles, but everything else remains the same. And so this really allows you to do robustness testing. How much time do I have? Am I almost done? 5 minutes? 5 minutes. Okay. And of course, you can take, I showed you rig transfer, so that allows you to transfer from one embodiment to the other, but this is an extreme sort of rig transfer where, think of it like you've got this video from the internet of something interesting happening, and now you want to say, well, here's an interesting video that I got from a dash cam. How can I actually get this into my fleet? How can I use this for validation? And so you can take one camera and start simulating the others. But I think, probably repeating myself, but these are all capabilities that you can easily get once you have a world model that is capable of producing set of pixels for self-driving. This is a particularly interesting case is because we've been able to also do some in-context learning for video diffusion models. And so we've been able to take scenarios that are unsafe or particularly weird. For example, here the car is suddenly stopped on the road. And then we're able to provide this scenario in context and then have the world model generate another scenario conditioned on a starting image. And so you want to say, well, so this is what you saw in the first image. This is the starting image. Can you generate a similar scenario here? And now the world model has to figure out how to place cars at the right place so that the scenario is plausible, but at the same time, it also transfers behaviors from one video to another. And so this is a particularly simple case where you're harshly braking, but now you can place it on the highway below all of these different highways going on top of you, and you can get the same scenarios, even though you might even have a different rig. For example, it's a different rig, but we are still able to simulate these scenarios. And I guess I'm getting towards the end, and so I thought I'll show you that we can also use it to do very, very out of distribution states, which hopefully we will never encounter in the real world. But sometimes regulators need to be given extreme test cases. And so I'll just end in just another minute and say that, so this is how we really think about evaluating an embodied AI product. Evaluation's actually, in a sense, harder than actually creating the driving model itself, because you have to think of all of these tail scenarios. You have to do them at scale. But there's another piece that I find very interesting in this space is the role of language. And so, of course, VLAs are everywhere in embodied AI, and people are taking VLAs and training them for all kinds of manipulation tasks. And I think language also has a big role to play in self-driving. And so, of course, LLMs, it's not surprising now in 2025 that LLMs are able to encode lots of interesting tail information about driving or what you should do, even if they don't tell you exactly how to drive the car. And I think language has a role to play in many different aspects of self-driving. So, for example, explainability is a big thing. There's many different ways you can provide explainability. One is through commentary, one is through question answering, and there are other ways as well. One way to do this is sort of done in a very sort of post-training scenario, is you train a driving model and then you add an LLM head to it. And now, similar to how visual encoders are taken, stitched together with an LLM, and now you have a model that is capable of captioning or answering questions. You can do the same thing here, where you can start providing commentary to the user, and you can start answering all kinds of questions. And of course, your outputs don't only have to be language; they can also help debugging your models. And so you can start asking it questions that can generate segmentation masks, bounding boxes, etc. So that's one role where language can play a part. Then, of course, you can do the way that a lot of people are doing it in embodied AI, which is actually build a VLA. And so we are able to take a language model and attach our, some components of our foundation model, our Wayve vision model here, and then train this on our driving data so that now you can not just output language, but you can also input language because you have this LLM. And so here is a demonstration of a VLA running, real time on the road, which is actually quite an impressive feat because there are obviously it has to be incredibly fast and incredibly safe. But what you can do now that you have a language model driving in the car is that this is in our simulator, and so you are able to give it actions to produce through language, and you can say, can you please stop behind the bus? Can you start overtaking the bus, etc. So these are sort of we don't use VLAs in our product, but from a research standpoint, it's very interesting to see from not just in terms of the AI, but also in terms of human-machine interaction, how people might start interacting with your cars. You're in an Uber and the car is driving rashly. You have a tendency to say, I have kids in the car, can you please slow down a little bit? And so we must have ways to interact with our models through natural language. And so there's lots of interesting research questions here. And of course, this is the thing that I'm sort of actively thinking about, and that I believe is the real way to use language models, is to have a reactive system like we already do in the car, and have a much more slower reasoning component that can interface with the reactive system. And the example that I like to give is, I'm at a supermarket, I'm in this self-driving car, it's raining, and so the self-driving car needs to find a parking spot that is close enough so I don't get wet. But at the same time, I'm impatient. I don't want this self-driving car to go round and round and round the parking lot looking for a space, right? And so it really needs to use its use its large language model knowledge to know what's the time of the day, what's the weather condition like, is it going to keep raining, for example, when I get to the store? Am I going in a time which is very crowded? And so, how should I sort of optimize all of these different inputs in order to make a good decision? And that's not something that needs to be reactive. The language model can plan for it and can sort of prompt a driving model. But how this prompting takes place can either be through latents, which I think is a quote-unquote natural way to do it. But another way to do it is to also do this through natural language, because that then allows you to have a single interface where a language model can talk to your driving model, but also you can have a human being talk to your driving model. And so there's lots of interesting questions which are truly multimodal in nature that I'm excited about. And with that, I will end. Thank you.